Okay, today we're going to talk about KINGSTAR's Tuning Console and how to tune a PID filter. This software basically offers a PID filter along with velocity feed forward and acceleration feed forward along with S-curve acceleration. We feel that that's going to handle well over 95% of all motion control applications. So what we're going to do here in the initial setup of this, you can see a motor off to the right. It has a 1 million count encoder. So as you can see in here, we set up the encoder resolution as 104.8576 against 360 degrees. And this is basically a numerator and a denominator. And you only have to set this up one time, and then forever you're working in degrees, at least for this. You could change it to whatever you wanted. If you wanted to work in meters, if you wanted to work in inches, you could do whatever you want. As soon as you set that up, you're good to go. Now, the way we prefer to operate is the drive is run in a very straightforward torque mode. You don't have to mess with the drive's tuning parameters. You don't have to look at all the different tools that drives can offer. In this case, you could have an EtherCAT network that has 10, 20, 40, perhaps 80 motors on an EtherCAT network, and you could have 6 or 7 different manufacturers, and instead of having to learn each of their tools and their idiosyncrasies individually, you just use this one tuning console and it does everything for you. So the first thing you're going to do is go in here and do a current test. Now when we hit this current test, you can see that the motor moves. What you're looking at here is simply some commanded torque. 50% forward, minus 50% reverse. So we were asking for 30 as a flat 30%, then minus 30%. We have a couple of ramps and a couple of different sine waves. If the red, which is the torque actual from the drive, doesn't match the black commanded, then you have a problem and there's no point in trying to set up a servo because it's not going to work. In this case, you can see it is following it. There's a little bit of delay, a couple of milliseconds that's done. That's the natural part of an EtherCAT network. But all in all, this is good. So now what we're going to do is we're going to work on a step response. A step response, and here I'll just click step. In this case, we're going to say, I want a 3 degree, this is position, I want a 3 degree command as a position. What you want your actual position to do is quickly start out from here and quickly approach the 3 degrees, overshoot a little bit, and then quickly settle out. Now, as you can see, all our parameters over here are 0, so nothing's going to happen. I can hit step all day and nothing's going to happen. What we're going to do now is have these buttons which allow us to very, very easily change values for KP and KD. We have no idea what values are really going to be needed in here, so I'm basically going to just say, associated with KP, just double it. The fact that it was already 0 just means that our software is going to go ahead and give it a value that would have given it 1%. As you can see, it's barely moving. We double it again, it's moving a little bit more. I can double it one more time, and you can see that it does make the 3 degrees, but it's very slow. And as you look down here under step time, you see 0.064. So it took 64 milliseconds before it peaked. That is, of course, very, very slow. A decent servo will be somewhere between 8 and maybe 15 or 20 milliseconds. Clearly, 64 milliseconds is very slow. So KP is basically thought of as response. As you increase KP, you get an increase in the response. This output will grow. KD, on the other hand, looks at the change in the error and would look, for instance, at the slope in this section of the line and say, we may not be at our target yet, but we are rapidly approaching our target, so maybe it's time to put the brakes on. And it basically works in conjunction with KP. KP is for response. KD is for stability. So right now I'm going to start to increase over here with a ×2. I'm going to increase the KD, which is going until we prove that the system is more stable. So I'm just going to continue doubling this until that output, as it is now, is starting to reduce. And once it gets below the line, I'm going to go back and do KP. And this is just an iterative process, but the key to it is you know exactly what to do. If you're above the line, I'm going to add KD for stability. I'm going to continue to add this. You're a little bit below the line, I'm going to double it and add KP. So if it's too small, you add KP. If it's too big, you add KD. We're a little ahead of it, so I'm going to double KD ahead. Now I'm going to start down up here on the 1.1. I'm going to use 10% up, and I'm just going to click it and click it. I can continue to do it. I am slowly but surely adding more KP. I'm getting more response. And you can look at the step time, which is down around 21 milliseconds now. Much, much better than it was before. I can do a few more 1.1s on this, and now I will add KD for stability and bring this signal back down. And we can do this until we start to lose the smoothness of the signal. Add more KP. We're getting better response. We're sitting here at 16 milliseconds. I'll put some KD on this to bring it back down. And now we're back where we were. I'm going to add some more response. We're down to 16 milliseconds. Every time we add a little more KP, we're getting better. We're down to 14 milliseconds. And we can just do this a little bit more and then put a little more stability on it with some KD. And now you can look at this. I'm just going to put a tad more KP on this. What you have here is a quick response, 12.5 milliseconds, and it pretty quickly settles back out. So at this point, I think it's safe to go out and run a traditional trapezoidal move. So here we have commands set up 7200 degrees. That is 20 revolutions. 18,000 degrees per second. That's about 3,000 RPM. And the acceleration is chosen to get up to speed in 200 milliseconds. And here's what you've got. So this is the move we commanded. We're going to accelerate for 200 milliseconds. We'll slew at top speed for another 200 milliseconds. And then we'll ramp down for another 200 milliseconds. The blue is our commanded velocity. The purple is the actual torque in the drive. Now this is the same torque that we are commanding on a tick-by-tick basis, but the drive is confirming that that's what it's giving us. And this is the instantaneous following error at every point in time. And the rate that we're running right now is shown up here, EtherCAT rate, microseconds. This is 500 microseconds. So every tick of our EtherCAT network is 500 microseconds. And every 500 microseconds, we pick a new commanded position to get this velocity where we want it. And this is the instantaneous error as we make that move. So during the acceleration, we've got somewhere in the order of 1.25 degrees worth of error. Top speed, there's just a little bit of friction in this motor. It's got bearings and it's got a seal which puts on a little bit. It's very close at this point, but we'll try and take some of that out. And then during the deceleration, we have a fixed error as well. So what we're going to do now to try and get rid of this, we're going to go up to KV. KV basically says, I'm running at a reasonable speed, just give me some assistance. Give me a few percentage points of torque output without requiring KP or KD to do it. So if I click on KV, you can see it puts up a series of control buttons, and I can just hit ×2. Again, it'll put in a value of 1% since it was 0. And we can just double this and double this until we see that is very close to just sitting on that line. Now we're going to move to KA. KA is for acceleration. During acceleration, right in this section right here, and you can read it up here when you put your cursor on it, it needs about 51% of the full scale output. So in order to get that, basically we're going to say multiply my 90,000, as in degrees per second squared, by the value I've chosen for KA and put that out. So that's exactly what it's going to do. And we're going to double it and double it until it starts to do something. I could calculate this, but it's just as easy to continue to double it. It's already moving. I'll do one more doubling. I'll now switch to 10% moves, and I can do a series of these. I can just click it a few more times, and then slowly, I might have gone too far on that one, so I'll back off by 1, and I'll go back by 1%, and I think that's as good as we're going to get. Now over here, the normally the Ka term works on acceleration and deceleration. We've chosen to separate these because the values needed are different. During acceleration, friction hurts you. During acceleration, friction hurts you, and on deceleration, friction helps you. So this is Ka again, but with a D on the end of it. It basically means during deceleration. So I can start to double him, and I can continue to move this until we start to see something happen. And there it is, it's moving. So now I'm going to go up by 0.1s, and I can do a couple of these, and our error just starts to go away. We still have some ripples in here, but all in all, we're looking at right here, we're getting an error of 1/2 of 1 degree. So at its worst case, even here, 0.55 degrees. You're off by about 1/2 a degree at top speed. So what we have here is a well-tuned servo loop, but we think we can do better. First of all, these edges are very sharp, and you can see it is commanding a great deal of current at this point, 90%. So these changes are very, very abrupt, and I don't know if you can hear it, but there's 4 individual bumps that you can hear while you're running this, and it happens to be these 4 peaks. So now what we're going to do is go to an S-curve acceleration, in which case we ramp up before we hit the full acceleration. So here's an S-curve. I'm not sure if you can tell, it's much quieter. This is a rough one, and this is the quiet one. Now, we paid a small price for this, however. The original move took 600 milliseconds. This move now takes about 620 milliseconds. You can see you don't have those sharp rises, but at the end of the day, this is so much smoother. We can probably tolerate an increase in our acceleration. So as I hit the S-curve, still very quiet, still very smooth. This will be slightly higher because we've increased the slope of this line, but now it finishes right around 600 milliseconds. So again, we're back. And what we're seeing now is a much smoother take on this. It's still down. If we look at the error, we're looking at 0.1 degrees here. In this case, it's 0.15 right up in here. Again, you're looking 0.12. So we're at somewhere on the order of less than 1/5 of 1 degree, and this is finishing in a reason. We have a very little error out here. We also have an I term if we needed it. We have a limit of 10% for the I term. What the I term does is, in a case where you have a small but finite error that you can't get rid of any other way, Kp times the error is too small to overcome friction. You can say, well, give me some integral where you integrate each and every tick, you add the error to the previous. Sooner or later, it becomes large enough that when multiplied by Ki, causes movement. So I'm just going to double this, and I'm hoping we can see some of that error way off to the far right. It is starting to go away. So this is the way we prefer to do this. We are now, I can turn this off. We now have a fully tuned PID loop, and we're in good shape. And the very next motor, even if it's a completely different manufacturer, will be able to use this technique. Thank you.